Hello. This is the continuation with our work on how to solve differential equations using Laplace transforms. Today we're going to look at not just one differential equation, but what if we have multiple differential equations? That's because with sorry, I need to adjust my screen here. There we go. With the aircraft, we actually have 3 differential equations, or even 6 differential equations that need to be solved. So the example that we're going to use today is a double mass spring damper system. We have mass M1 and mass M2, and this mass is connected with a spring to a hard wall, and this mass is connected to the other mass with a spring K2. Both have forces applied to them, potentially, and we track displacement x1 and x2 of the masses. So drawing a free body diagram of mass M1, we have K, spring constant, times the displacement x. We have the force applied here, and then we have the spring force, which is the relative displacement between the two masses. So if mass M2 moves further than mass M1, then we get a force. And then mass M2 can have an applied force F2 as well. So sum of the forces equals mass times acceleration, and we get, for mass 1, we get F1 minus the spring force backward, spring force forward to the other mass, and that's equal to the mass times the acceleration. Mass 2, same thing, F2 minus the spring force equals mass times acceleration. So putting those in more standard form, using the double dot formation and collecting terms here, so we've got the x1 term here, the x2, and then here's x1 and x2 over here. We can see that we've got 2 differential equations, but they're coupled because there's x1s here and x2s in this equation. There's x2s and x1s in this equation, so we have to solve both equations together. The initial conditions we're going to initially look at, I guess that's a double initial, are that the mass is still, and it's in 0 position, both for both masses. So here and here, both x2 dot and x2 are 0 at time 0. Same thing for x1. So what we're going to look at first is the homogeneous solution, which is the unforced solution. So there's 2 ways you can solve this, and you're looking at my kind of scribbled notes. You can Laplace each equation individually, and I'm going to show you that on the next page. So you just take the Laplace of this equation for x1 and this equation for x2. You have 2 algebraic equations and 2 unknowns. It's easier if you put it into matrix form to start out with, because typically once you get several equations and several unknowns, you end up in a matrix anyway. So we can put this in a matrix form where we have a vector of unknowns, or vector of states, x1 and x2. And so here we have m1 times x1 double dot, and then we have another matrix here that contains the stiffness k, and those multiply x's, no double dots. And of course f1 is 0 and f2 is 0 for our homogeneous solution. So this is called the mass matrix because, for obvious reasons, it has the masses in it, multiplies the double derivatives. This is called the stiffness matrix because it contains the spring stiffnesses, multiplies x, no dots. If we had dampers in here, which I didn't include because it makes it more complicated, we would have a damping matrix as well that multiplies x1 dot x2 dot. So using differential equation methods, the solution for the homogeneous equation, the homogeneous solution, is to try these 2 solutions. We say x1 is a e to the st, x2 is b e to the st. The whole idea is you try this, and if you can find s's that make this work, then you have a solution. So that's what it says here, find s to make this work. A and b are constants, and we'll see how those work in a bit. You might be tempted to say, well, let's say x1 is e to the alpha t, and x2 is e to the beta t. That is, you don't use the s for both of them, like here and here. You say, well, what if we can have two different values of the Laplace variable in the solution, or the variable s? Doesn't work, because if once you substitute in, remember we have to cancel the e to the st terms all the way across the equation. And if you have x2 in terms of beta and x1 in terms of alpha, you can't do that cancellation. You'll see that on the next page here. So this is method 1, where you just Laplace each equation separately. So if you Laplace x1 double dot, you get s squared a e to the st, so that's x1. Here is x1 again, no derivative, so you just get a e to the st. And then x2 is b e to the st. And as we talked about up here, if you use s for both, then you can cancel the terms here and end up with an algebraic equation for s. Same thing for equation number 2 here. We get x2 double dot is s squared times b. x1 is a, and x2 is b e to the st. So we end up with two equations, algebraic. We can solve for s and a and b. Or, looking back at the matrix form that we had up here, you can Laplace that just as well, because the derivatives inside this box here just Laplace, and these variables Laplace. And in fact, even if we don't have a homogeneous solution, we can Laplace everything. So here's the Laplace of the double derivatives. Here's the Laplace of the single derivatives. Doesn't matter that it's in matrix form. We just Laplace each term in the state column vector here. If you do the Laplacing here and then cancel out the e to the st's all the way across in the matrix, or you take this set of equations up here, now it's algebraic, and we put it into matrix form, we both methods give the exact same matrix problem, two equations and two unknowns. First equation here, second equation, end up in the matrix. So if we combine this term here with this term here, just add them together, we get a matrix with the s's and then our unknowns a and b, and it's still the homogeneous solution, so we get this. Alright, so if for some reason the determinant is not 0, which is usually what we hope for, then we can solve the above, and it gives a is 0 and b is 0. Because the right hand side is 0, you invert the matrix, multiply by 0, and you get 0. That's useless. It's called the trivial solution, but it's really a useless solution. So again, remember the whole premise is we try this and see if we can get something useful out of it. So the other option is to say, well, okay, what if the determinant of that matrix is 0? Then we can't invert it and we don't get the trivial solution. So if you take the determinant of this, you get this thing here times this thing here minus this thing here times this thing here. So that's what I've done here. Determinant equals 0 because that gives us a possible solution. And this is what's called the characteristic polynomial. Just like we had for one equation, this gives us roots that characterize the system behavior, the motion of the behavior of the system. It's a fourth order polynomial because here we have s squared times s squared, so we get 4 roots. These are the roots of the problem. They're the eigenvalues, just like before. These tell us what the motion of the system looks like. And our solutions are x1 and x2 is a e to the st, b e to the st, and the s's are these different roots. Alright, so that's the solution. The once you know Laplace transforms, it's a bit easier to use Laplace methods to solve this. Same procedure that we did before, where we Laplace each term. And so here's the mass matrix. Here's x double dot, stiffness matrix, x. I think I made a mistake earlier when I was talking about this here. With this method number 2, I didn't Laplace these. I simply plugged in and took the derivative, and that's how we got the s squared here and here. So if I said Laplace earlier, that was wrong. This is just substituting in just like we did here, but in the matrix form. Okay, if we Laplace, we Laplace the double derivative with the 0 initial conditions that we talked about, and we get s squared times the Laplace. You Laplace x1, you get x1 here. You Laplace f, and you get capital F of s. So I just went through and Laplaced each term in the equations here. These are constants. These are numbers. So just like before, they go along for the ride. The Laplace of a constant times a function is just the Laplace of the function. So once we Laplace this and then factor out the state vector here in terms of Laplace, we end up with a matrix here. And that matrix looks exactly like the matrix that we had up here when we used the traditional differential equation solution technique. So the Laplace method gives us the same matrix here. And if we look at solving this, so now we're in the Laplace domain, so it's an algebraic equation for this, for the x1 and x2. Kramer's rule says that x1 is the top, the matrix, the A matrix here, or this matrix right here, with the first column replaced by the right hand side. So that goes in the top, and then the bottom is the determinant of that matrix. And then the second unknown is the determinant of this matrix with the second column replaced by the right hand side. And again, you divide by the determinant. So notice again, the characteristic polynomial is the determinant of that exact same matrix. And the roots of that give the motion. And the determinant is the same thing that we had before. And remember with Laplace transform methods, the denominator of these functions is what we use to do partial fraction expansion. We're going to go through that in a minute with numbers. So those roots of that denominator polynomial are just like the roots we got earlier with the single mass spring damper system. Okay, so let's stick in some numbers because it makes it easier when we're talking about the roots. So let's say both springs have a spring constant of 10 and we have a mass of 2 for both masses. So I substituted into the matrix up here, and we get this matrix here with the numbers plugged in. We're not going to specify the input yet. With the Laplace method, you can handle all kinds of inputs. With the differential equation method, you have to find the homogeneous solution and the particular solution. So this, I think, is more straightforward. Take the determinant, so we get this thing times this thing minus this thing times this thing. So that's what I'm showing in this line here. Work the algebra and you end up with this polynomial. Set the determinant equal to 0 to get the roots, because those are what show up in the partial fraction expansion. All right, this is the denominator of using Kramer's rule up here. It's just the determinant of that matrix. And so here's the roots that you get if you plug that polynomial into your calculator or MATLAB and factor it out. And so what that means is the solution, x1, which is equal to that numerator thing that we get by replacing the columns, divided by the determinant So those roots are the roots of this determinant polynomial that we just talked about. So those roots that we found up here go into the denominators of the partial fraction expansion, because you can factor this denominator into the 4 different factors. So here we got s to the minus 3.618i, s plus, s minus 1.384 So each one of those roots shows up here, 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 and here when we're doing the partial fraction expansion. So the solutions then, if we do the inverse Laplace using the tables on each of these terms, we get k1, which we haven't found yet, but we can. We know how to do that. We get k1 e to the 3.618i. We get the negative root here. We get the other positive root here and the other negative root here. And so you get a term in the solution that corresponds to each one of the roots. Just like we did when we had the single differential equation. We had 2 roots and we got 2 terms. So now we look at this and say, what kind of motion do we have with this solution here? We don't even need to find k1, k2, k3, and k4. We can simply say, well, what kind of motion we get. Notice we have e to the some number times I. So this is an imaginary root. And we saw with the previous lecture that if you have an imaginary root, you get oscillatory behavior. And this is undamped. There is no e to the minus 3t term that multiplies these, because we didn't have any damper in the system. So these are oscillatory, and the frequencies are those roots of the characteristic polynomial, the imaginary parts. And again, that's because e to the something I times t turns into cosines and sines, and this is the frequency in radians per second. Because the angle inside the sine has to be radians, we're multiplying by time, so this has to be radians per second. So to recap, go back up here, we have, way back, we got 2 differential equations. We can substitute and solve differential equation form, or we can Laplace them, which is more straightforward. Put them into a matrix, Laplace each individual derivative. We end up with an algebraic problem. We solve the algebraic problem using Cramer's rule, which gives us the determinant of the matrix, which gives us the roots that show up in the solution here. Notice, this is really important, that we have 2 different frequencies. That corresponds to what's called 2 modes of motion. What does that mean for the system? It says that x1 and x2 oscillate with 2 combined back and forth motions. Let's go back up to the picture of the system. What that means is that this mass can oscillate back and forth. This mass can oscillate back and forth. And the 2 masses relative to each other can go forward toward each other and away from each other. And so we get the 2 different frequencies of motion. Or you can think about it as there's a frequency of m1 and m2, but that's not true, because each of the solutions, x1 and x2, have both frequencies involved. So you can have both masses moving back and forth together, or you can have the masses moving toward and away from each other. And that's where you get the 2 different modes. This is important because an aircraft with 3 or 6 degrees of freedom will have 3 modes of motion or 6 modes of motion that we have to deal with. Alright, there's one other thing I want to show you. There's a form that's the standard form for solving multiple differential equations, and it's what's called state-space form. There's nothing magical about it. It's just everybody's agreed that this is a standard form that we can put equations into, differential equations. And once you do that, then the solution's known ahead of time because the standard form leads to standard solutions. And there's all kinds of software, including MATLAB functions, where you can just plug in the matrix form that you get from this, and you automatically get the solution. You don't even have to go through all the stuff we've been doing. It just does it automatically because you put it in standard form. Okay, the first key is that you have to get the problem into all first-order differential equations. That means only one derivative in each equation. So how do we do that? Because here we've got x1 double dot, and here we've got x2 double dot, and yet we need first-order differential equations. Here's the trick. x1 dot, x1 is position, so x1 dot is velocity, so let's just call it v. No dot because it's called velocity. x2 dot is the change in x2 position, so let's call it velocity 2. If we do that, rename x1 dot and x2 dot, then x1 double dot becomes v1 dot, x2 double dot becomes v2 dot, and now we have first order differential equations. No big deal, it's just in terms of velocity. But if we wanted to calculate position, which is included in here, we need to know, well, how is position related to velocity? Well, that's exactly these equations here. The relationship between the velocity, essentially the definition of v1 and v2. So what we've done is replace 2 second-order differential equations with 4 first-order. Here's the first one, here's the second one, the third one, and the fourth one. So we haven't really lost any information or changed anything. We've just renamed some of the variables to get it into this standard form that only has first-order derivatives. So this next thing you do to get it in the right form is you get the derivative all by itself on one side of the equation. So I've solved for v1 dot and v2 dot. This is important because we're going to put all the derivatives on one side of our form and everything else we shove over to the right. So there's 2 key steps to this. The first thing you do is you redefine more than first order derivatives and call them new names, so you only end up with first order derivatives. And then you put all the derivatives on the left side and everything else goes on the right. So let's look at that. Here's the first equation for v1 dot from up here. So we're taking this equation here. Oh, sorry, this one here. So that's going to go in here. Connected the dots there pretty well, huh? So v1 dot is equal to 0 times v1. So I'm just putting in this equation here. It's going to be equal to k1 plus k2 m1 times x1, 0 times v2, and k2 over m1 times x2. And then how do I handle this f term? Well, I put it in a separate matrix here where these are my inputs and these are my states. Makes sense because we separate out the inputs because we haven't specified them yet. This is how the system behaves. This is the dynamics. So the next equation I put in here, and you can choose whatever order you want, but the next equation I put in here was just the definition of v1. Remember, we have derivatives, dots on this side, no dots on this side. So this equation says x1 dot is equal to 1 times v1. So that's the definition of x1 dot. Simple equation, but we have to include it because it tells us how x and v are related. Okay, this equation here, put in here, is the equation for v2 dot. Again, you can see why we needed the derivatives on the left side because we're sticking them into the left side here. That's going to be equal to 0 times v1 because there's no v1 up here. And then we get k2 over m2 times x1 and k2 over m2 times x2. So that's this term here and this term here. And then we put the forcing function of the input over here on the right side. Notice now we've put this into a nice neat package where we have derivatives, first derivatives on this side, no derivatives on this side, And it's in terms of a nice matrix where we call this thing the A matrix. It multiplies the states v1, x1, v2, x2. And this thing the B matrix because it multiplies the inputs. And this is the standard form. This is called Statespace form right here, that you have a vector. We're going to call it x now. It's a state vector. So on the left side you have each state derivative, and on the right side you have an A matrix times the states x, and the B matrix times the states, the f's, which are in this U vector here. So what do we do with this form? To solve it, we haven't really changed anything. We just rearranged and put it into a different form. But we can Laplace it. So a derivative turns into an s. And then the right-hand side, their A and B matrices are just numbers, so they go along for the ride. So we Laplace x, and we Laplace the inputs. And then we move this term over to this side because we want to collect all the s's because we're x's, because we're solving for the x's. So we get si minus a times x is equal to b xu. And then this is a matrix, right? We've just moved some of these matrices around and collected it together. So you use Cramer's rule, kind of cramped over here, and you get si minus a. You get this matrix in the denominator because we use Cramer's rule to solve for this x vector. So notice that the si minus a determinant of that thing is in the denominator, so that's going to be our characteristic equation. Let me show you how that works. We'll plug in the same numbers we had before. So there's our spring constants and our mass. And in state space form, it's spread out now because we have 4 equations instead of 2. And then this is our A matrix. And then what we want is the determinant of Si. I is the identity matrix. Minus a, because that's what shows up in the denominator if we use Cramer's rule to solve this. But notice that this is the eigenvalue. It's the definition, the math definition of eigenvalues of the A matrix. That took all the energy I have for the rest of the day to write that. Hopefully you can read it. So the for the eigenvalues of the A matrix, it's Si minus A, definition. So you can go into MATLAB and enter the A matrix and tell it to find the eigenvalues of this A matrix, and you automatically get the roots that we got up here for the roots of this characteristic polynomial using the non-state space form. So that's what's on the next page here. Is I go into MATLAB and I create the A matrix. I was doing something else that had the A matrix, so I had to call this ABAB just for keep it separate. I didn't want to overwrite something else I was doing. So there's my A matrix. Matches the A matrix up here. And then I simply use the MATLAB command eig. And look at this, we get the exact same roots of the characteristic polynomial that we had using the non-state space form. And we should, because we didn't change the equations, we just rearranged them to get them into this standard state space form. Again, the nice thing about this, notice that now we can use a MATLAB function to find the roots rather than having to find that polynomial. It automatically finds it for us. So we can get the roots. So any problem, let's say we had 100 masses, that's a lot, all connected together with springs. We wouldn't have to Laplace all 100 equations. We would simply redefine the velocities. So we'd end up with 100 positions and 100 velocities. So we'd end up with 200 equations. We throw it all into matrix format because that's how it's easy to keep track of, and we don't have to do anything. From that point on, We found out what our A matrix is because we put it in Statespace form. And then we simply find the eigenvalues of that matrix. We don't have to go through the partial fraction expansion or anything. We just say Eig of the matrix and we're done. We know exactly what our solution looks like. And in fact, in MATLAB, you can feed the A and B matrices and do all kinds of things. You can do partial fraction expansion, solution, everything related to those differential equations. I think I will do that in another lecture, so we're going to stop here where we've covered how to solve more than one differential equation at a time.